Hello, this is my presentation over the automatic identification and digitization of features using remote sensing data for GSIN 6386. This will be an investigation of the methods to automatically create vector data from aerial imagery or remote sensing data. One example is automatically digitizing the edges and or the center line of a road through automatic methods instead of manually digitizing. So the basic concept is that you can take an aerial image that consists of roads, vegetation, or any type of land cover, and rather than performing the tedious task of manually digitizing everything, you can use an automatic process to export the features in a vector format. The first literature review that I will go through is an article named "On the Accuracy of Glacier Outlines Derived from Remote Sensing Data." A team of multiple analysts digitized glaciers multiple times, and each analyst was required to wait 24 hours between each digitization. The analysts had to document how long it took them to digitize the glacier outlines, and they were able to use different reference sources or whichever software they preferred. This is the study area for the glacier article. It's involving an area of the Chugach Mountains in Alaska, as well as the European Alps in parts of Switzerland, Austria, and Italy. It's important to know how accurately the glacier outlines can be mapped because changes in the glacier size are an indicator of climate change. There needs to be rules for defining the perimeter. For example, the hydrologists prefer to separate the ice cap into different drainage basins, but a glaciologist will keep the ice cap as one single unit. So there needs to be a consensus and agree on how to digitize certain parts of the glacier in order to be consistent on how the outlines are digitized. Some other issues are that the clouds, shadows, or debris that covers the glaciers can cause difficulty in the outlining. This is one sample image of one of the glacier study areas. You can see that there are multiple outlines in different colors that each analyst has digitized the outline. And you can see that for the most part, the outlines are similar and consistent. However, there are some areas where there are differences in the outlines. For example, on the right side, there's a big difference of 600 meters based on how each analyst will interpret the outline of the glacier. For this project, the analysts were using Landsat thematic mapper data along with higher resolution 1 meter ICONOS data. The data needed to be from the same date or within 1 week because of the snow conditions that can change. One issue is that the higher spatial resolution can show new details, which can mean the analyst can change his interpretation of the outline. Another issue is that there is a low contrast between the edge of the glacier and the surrounding rock in the visible and near infrared spectrum, which can also lead to the perimeter of the glacier being difficult to decipher. And one should also note that the area of the glacier can vary depending on the spatial resolution of the data used to draw it. So in other words, if the higher resolution shows more details, the analyst may digitize the outline differently, and this can result in differences in the area. And here is an example of an area of the glacier where there is some issues that can cause differences in how each analyst will digitize the outline. For example, on the left image, there is debris and soil covering much of the glacier, which can make it difficult to determine the outline. And on the image on the right, there's a difficulty in determining the terminus or the endpoint of a glacier, so one analyst might digitize it shorter or longer than another one. And here's a summary of the different tasks that the analysts were given. For each of the different regions, they were asked to digitize the glaciers at least once, and in most cases multiple times. Here's another example of the glaciers where the different color outlines show each analyst determination of the outline, and also you can see the white outline, which is an automatically derived outline, and this is based on the band ratio method. You can see that the analyst outlines is more curvy and following the natural pattern of the glacier, while the automatically generated outline is having sharp angles, 90-degree angles. So the shapefiles of every analyst outlines are superimposed on the images in a GIS, and the total area, mean size, standard deviation for each glacier are calculated. And the analyst outlines are also compared with the automatically derived outline. And here's one more example showing the comparisons between the analyst outlines and the automatically derived outline. And because of the issues and that the outlines are a subjective choice, it is impossible to have a perfectly correct outline, since there is human error involved as well as the choice of how to digitize the outline. The automatically generated outline was made using the band ratio method. This next source is called Using the Band Ratio Classification Method to Detect the Regions that Need to Remove Sedimentation in the Tigris River. The benefits of the band ratio method are that this method uses the division of a digital number values in one spectral band, which correspond to the digital number values in another band. The spectral characteristics of features being collected is more consistent despite different illumination conditions. So by using the band ratio method, you eliminate the problem of shadows, and features in the imagery will show the same spectral signature despite it being in a shadow or not in a shadow. The next literature review that I will go through is an article over imagery of the Tigris River using Landsat satellite ETM image. There are 3 classes for the water created: a shallow class, an average, and a deep water class. The shallow areas are made darker, and the object of this project is the long segments where sediments need to be removed are identified. And the other reason for this project is that dumping of municipal and industrial waste into the river without treatment is occurring in this area, and it's talking about Baghdad. The steps performed in this project is first that the band ratio technique is applied by using the ratio of band 3 divided by band 5. Next, a normalization technique is performed to assign the 3 different water classes, which are shallow, average depth, and the deep water class. Next, the raster to polygon tool in ArcMap is used to create the water bodies. The water bodies are then selected, and everything else from the image is removed. And lastly, the area of each water class is calculated, and these data is used for analysis of the shallow areas that contain a lot of sedimentation. As mentioned, there are dumping of sediments directly into the Tigris River. Here is the beginning image of the Tigris River that will be used for this project. The original image was converted using the band ratio method, and the band 3 was divided by band 5 in order to make the water bodies stand out. The next step in the process is that the surrounding background area and everything except for the water bodies are removed from the image. The raster data is converted to a vector format by using the raster to polygon tool in ArcMap. This is a summary of the results done by this project, where first the 3 water classes are showing the areas and number of pixels for each class, and the second table shows the areas and number of pixels of the shallow, average, and deep water after applying the band ratio method. The next literature review will be in a 2016 article, which is titled Remote Sensing Methods for Power Line Corridor Surveys. The next literature review that I will go through is identifying electric transmission structures automatically from the aerial imagery. This is based on the geometry of the towers, and the purpose for this is monitoring vegetation along the power line corridors, identifying tree branches that may need to be cut, and checking for other obstructions near the power lines that can be hazardous and causing disruption of the electric service. And this article discusses various sources of data, including satellites, fixed-wing aircraft, helicopters, UAVs, as well as ground vehicles. The first data source that is discussed is the synthetic aperture radars, which are imaging sensors that operate in the microwave region, and the wavelengths are from approximately 3 centimeters to 25 centimeters. The SYarter system transmits microwave radiation, records backscattered signal from the target, and creates a 2D image-like presentation of the illuminated area. The benefit of using the microwave radiation is that it can penetrate clouds and can be used in any weather conditions. This example is showing the original imagery, and the object of this paper is to identify the transmission towers automatically from the imagery. And here's another view of the imagery where the bands are modified to better show the transmission towers. And the last step is that the towers are actually extracted, so everything except for the towers is removed. From another one of my sources, which is titled Raster Scanning for Operational Digitizing of Graphical Data. It's a 1982 article. It's talking about extracting vector data from raster data, and you can see the first image is the raster data structure, and the second image is where the image is skeletonized as one example of the conversion. You can see that the ones in the image are simplified to form one single line instead of a line that is more than 1 pixel wide. And finally, the third image is the resulting line in a vector format. This next source that I'm using is a YouTube video where the narrator is talking about the benefits of the band ratio method, and he is trying to find the best combination that will show the different features despite the shadows that may be involved in the imagery. So he's trying to find the band with the highest reflectance and divide it by the band with the lowest reflectance. For example, he's taking for the grass, band 4, which has a high reflectance, and divide it by band 3, which has a low reflectance. And for the soil, he's using band 7 divided by band 1. And for the water, band 1 divided by band 5. As an example, I have used the imagery from the previous assignment of Houston, and I'm going to apply the band ratio method in ArcMap. So here's the original imagery, and here is the resulting imagery after I use the band ratio method. There's a tool in ArcMap which is called the band arithmetic function, which is in the image analysis toolbar. And as an example, I have divided band 4 by band 3. The next source that I'm reviewing is an article that's called The Automatic Break Line Detection from Airborne Laser Range Data. It's a 2000 article. The object of this study is to detect what is called a break line, which is a break in the elevation or a transition from a flat area to a sloped area. And in these images you can see that the break lines are created, and each pixel in the image is going through an algorithm which will compare one pixel to all of its 8 surrounding pixels, and the pixels that are sloped can be determined as a potential edge or a break line. In this image, you are seeing the automatically created break lines that are compared to photogrammetrically measured break lines, and the consistency of these two images is very good. The photogrammetry image is going to be more accurate, however it's more time consuming to create the photogrammetrically measured break lines.